that number? 1850. Okay? So all these will be taken correct. My answer over here when this is 0.91 was 1830. So you can see that the answers that I get from students can vary a little bit, and I have this margin of error that I mark all correct. So that's your final answer. We still have some time, so I'm going to go into the next topic, which is your heat exchanger analysis 2. I'm going to cover that so that we have lesson to cover next week. And why do I need that? Just because for next week, we'll be discussing some examples. The story goes this way. Because Glasgow, they have tutorials here. Glasgow, Scotland. So they have tutorials for heat transfer module, but over here there isn't. So for their tutorials, they have what they call revision examples here. So I plan to discuss some of these revision examples with you in the next lecture, because you don't have tutorial, right? So in order for me to put that in, I need to cover more of the materials for the next lecture so that I have some time to discuss the revision examples. So this next topic is actually the last one in heat exchanger. It talks about something very interesting. Now, if I were to take the example of a parallel flow, and you know a parallel flow is going to look like this, T versus X. X is the length of your heat exchanger, T is the temperature. And I'm going to label this difference over here as your delta T1, and that difference over here as your delta T2. And we already seen your LMTD expression, delta T1 minus delta T2, divided by ln delta T1 over delta T2. So this can only be found if you have all your inlet and outlet temperatures, both for the cold and the hot fluid. Only then that you can find what is the LMTD. So this is an important part. When you look at the question, look at it. Am I given all the inlet and outlet temperatures? If you are, waste no time. Stop using LMTD method. Right? If you're not given at least two of them, if you're not given two of them, that means you're given two, but not the other two. So it can be any of these two. There are 1, 2, 3, 4 inlet and outlet temperatures. If any two are not given, usually it's kind of like one over here and the other one over there that's not given. If you're given 3, it's still okay. Yeah? If you're given 3, you can find out the third temperature. You can find it out using the expression, because we know that this hot fluid will transfer its heat to the cold fluid. So actually, your Q hot will be equal to Q cold. And that expression, m dot HCH, let me label it, THI, TH naught, TC naught, TCI. So because QH is equal to QC, that means this would be equal to m dot C, CC, T, C0 minus Tci. So if you are given any three temperatures and all the rest of your m dot and your c's, any three temperatures and all the rest of this, you can find out the remaining temperature. Alright? So if you are given this, say any of the three temperatures, maybe this, and that. And you can use this equation to find out this unknown. If you are not given any two temperatures, might it be inlet or outlet? Let's see what's going to happen. Let me take an example of the case of this side that is not given. These two temperatures, TH0 and TC0, they are not given. So this one here is unknown. I call this one here unknown X. X symbol or nothing relating to this X over here. So my LMTD, if this were to be given to me, my LMTD, this value, I could simplify this. This ln fraction is actually the same as ln delta T1 minus ln delta T2. This denominator is actually the same as that. I do a cross multiplication, delta Tm ln delta T1 minus delta Tm ln delta T2. And bring this to the other side, that will be minus delta T1 plus delta T2. If I was to be saying that this term over here, delta T2 is unknown, and I express it as X. Now this whole thing here will be known. I call it a constant, say constant K1. Minus delta Tm, this is known. Ln X that I don't know, minus this term that I know. So maybe I combine this with that and call it a K2 plus X. This is unknown, delta T2 equal to 0. If there's a number here, ln X plus X. How do we find X? What sort of mathematical tool will you be using to find what is the X number? If I give you these numbers over here, this K2 could be 3, this one maybe 1. How do you solve this kind of equation? One unknown in the equation, is it possible to find out what is X? This kind of equation is what we call transcendental equation. Transcendental equation cannot be solved analytically, can only be solved using numerical methods. Alright? So, does that mean in my heat transfer module, Dr. Tan is going to bring in numerical methods? No, I'm not. In fact, I want you to learn from here that if you're faced with a question, that they didn't give you two temperatures, might it be given outlet? Please don't use LMTD method. Right? And if you don't use LMTD method, then what method would you be using? You use a method that we call effectiveness NTU method. NTU doesn't stand for Nanyang Technological University, no. It stands for number of transfer units. Number of transfer units. And we'll be seeing that in the following. This epsilon, yeah, epsilon, but we read it as effectiveness. So in some textbooks, they write effectiveness, NTU method. Again, when would we be using effectiveness NTU method? We'll be using that when two inlet or outlet temperatures are not given in the question. Then we use this method. If three are given, You still can use LMTD method. Obviously, if 4 are even, all your inlet and outlet temperatures, and waste no time. Use LMTD method. So that's somewhat explain why this is the reason. In heat exchanger, you'll be given sufficient parameters here. For example, your overall heat transfer coefficient or your surface area in order to help you to solve that. But what I want to highlight again is this capital letter C, capital letter CC, and capital letter CH. That's your specific heat rate for the hot side and the cold side. Let's have a close look at this case over here. This case has got a heat exchanger that's flowing in the opposite direction. So it's a counterflow heat exchanger. And particularly, we are interested in something. We're interested in finding out what is the maximum possible heat transfer rate that's called Qmax. Now we have seen before, Q is equal to m dot C, maybe not for cold, but generally. So m dot C and your temperature difference. That's how you find your heat transfer rate. And this m dot C is actually the same as capital C delta T. So what we're interested over here for this counterflow system is that if we take a small little slice over here, we know that this small dq heat will transfer from the hotter side to the colder side at this bottom over here. So if I equate that energy, that means my capital CH, my heat capacity rate for hot fluid, dTH must be equal to capital letter C dTc. So they must be equated together, right? They must be the same. Whatever heat that's transferred from the hot must be whatever heat that the cold is getting. So if we consider the case where my specific heat capacity for the cold fluid is smaller than this, my heat capacity rate for my hot fluid. If this is larger than that, that means CC. Sorry, if it's smaller than that, CC is smaller than CH. Could you see that in order for them to be equal to each other, my dTc must be greater than dTH. Did you see that? In order for them to be equal to each other. If I say that this is smaller than that, then this must be smaller than that one. So it's sort of like this is small, and if this is larger, right? And correspondingly, this one must be small, and that one must be larger, in order for them to be equal to each other. Okay? It must be that way. So that's to say, my Qmax over here would be equal to Cc multiplied by the temperature difference. And this temperature difference, delta T, in order for me to find out what is my Qmax, this temperature difference would be the highest temperature minus the lowest temperature. It works for counterflow and parallel flow. It will work the same way. So my Qmax will be equal to Cc if this Cc is lesser than Ch, multiplied by the large temperature difference, the largest temperature difference, this overall one. this from the highest temperature to the lowest temperature. That is your THI minus TCI. So it kind of makes sense here. This is the maximum amount of heat that is transferable from your hot fluid to your cold fluid. Qmax must be equal to Cc multiplied by this huge temperature difference. That is for the case when Cc is lesser than Ch. Please correct those in red. I think your notes there's a mistake, right? The one that is in red color. This H, C. If you have a case where your CH is smaller than your CC, then your Qmax over here will be equal to CH multiplied by, again, that is your maximum temperature difference, THI minus TCI. So we can develop a generalized form. The generalized form says that if you want to find out what is Qmax, that will be equal to the minimum of your Cmin multiplied by the maximum temperature difference. This Cmin over here can be equal to Cc or Ch. And in order to find out which one it is, you'll be given your mass flow rate and your specific heat capacity. Mass flow rate, specific heat capacity. You'll be given these values in order to help you to decide which one will be the smaller value, so that you'll go for that one and call that as a Cmin. That will be an example to show you how to do that. Okay? But for now, the theory part is that way. In order, this equation Qmax is equal to the Cmin, and we don't know which one will be minimum. We need to calculate it out, and then we'll know which one is minimum. And after that, take that minimum multiplied by the maximum temperature difference. I want to explain this part. I want to explain this part before you go. This part here, because for some people it's actually hard to understand, so I'm going to explain this. So if I have counterflow again, THI, TC naught, TCI, TH naught, is temperature versus length. The heat that's transferring from the hot to the cold fluid, that will be Cc multiplied by TC naught minus TCI equal to CH THI minus TH naught. Alright, just two more minutes. I know time is up, but just 2 more minutes, okay? Because just want to finish off this slide. Yeah, 2 more minutes, okay? Yeah, keep that for 2 more minutes, just 2 more. If Cmax is equal to Cc, that means Tc naught will be equal to Thi. So what that means is that if this cold fluid over here, because this one is for cold fluid, if my cold fluid, that heat capacity rate is the maximum between these two fluids, then actually this Tc naught here, it will start to approach my Thi. Why is it so? That's because if you have this Cc over here as your larger value, then if the heat exchanger is very long, then what's going to happen is that this Tc naught will tend to Thi. Right? So it exits almost at the temperature of your inlet hot fluid. So Cc Thi minus Tci, it will become the flowing rate. So you could see that this term now tends to this term over here. And if I were to take this fraction by taking CC divided by CH, take that fraction, equal to THI minus TH naught. Right, just bringing this thing over to the left-hand side. So for C max, that's equal to CC. Your TH is suggesting that your THI minus TCI is smaller than THI minus TH naught. And we know that this is not possible. Why is this not possible? Because your THI minus TCI should be your maximum value. Where is it in your graph? THI minus TCI. This should be your large value. But how could it be smaller? And that's why for your Qmax, you can never be equal to this following form. It can never be equal to that, but rather is equal to C min multiplied by THI minus TCI. That is your Qmax expression. Okay, so we'll continue from here next week, and I'll bring in some examples so that you could see some of these, how do we go about making use of that. I'll see you next week. By the way, there is this attendance sheet, so I'll still pass it around, right, so that you can sign it.